Download this code from codegive.com, link in the description below. OK, buckle up. We're about to dive into the wild world of experimenting with custom math for neural network tuning. This is an advanced topic, so I'll break it down step by step, providing code examples in Python, using NumPy and potentially TensorFlow/PyTorch for illustration. We'll explore the motivation behind doing this, potential ideas, and the considerations for making it work. Why bother inventing new math for neural network tuning? Let's start with the why. Neural networks are fundamentally based on linear algebra, calculus, and probability. The core operations, matrix multiplications, activation functions, gradient descent, are well established. So, why deviate? Optimization bottlenecks, standard gradient descent and its variants, ADAM, SGD, etc., can get stuck in local minima, plateaus, or saddle points. Custom math might provide alternative ways to navigate the loss landscape. Hardware acceleration, certain mathematical operations are more amenable to efficient execution on specific hardware, GPUs, TPUs, or even specialized ASICs. A new mathematical formulation might unlock better performance. Regularization and generalization, novel mathematical constraints or transformations might act as implicit regularizers, preventing overfitting and improving generalization to unseen data. Exploration and understanding, sometimes, simply experimenting with different mathematical building blocks can lead to a deeper understanding of how neural networks learn and what factors influence their behavior. Sparsity, a new math operation could be introduced to promote sparsity in the network's weights or activations, leading to smaller models and potentially better generalization. Novel architectures, completely new mathematical foundations could inspire entirely new neural network architectures that are fundamentally different from current models. 2. Areas where you could experiment. Here's a breakdown of areas where you might consider injecting custom math. Activation functions, instead of ReLU, sigmoid, or tan, you could devise a custom activation function with unique properties. Loss functions, beyond mean squared error or cross entropy, you could design loss functions that are more sensitive to specific types of errors or that incorporate domain-specific knowledge. Weight initialization, standard initialization methods, Xavier, He, aim to prevent vanishing/exploding gradients. You could explore custom initialization schemes based on new mathematical properties. Optimization algorithms, instead of gradient descent, you could create a completely new optimization algorithm based on different mathematical principles. This is the most complex, but potentially the most rewarding. Regularization techniques, beyond L1/L2 regularization, you could devise custom regularization methods based on new mathematical measures of complexity or smoothness. Layer operations, you could invent new types of layers with custom mathematical operations inside. For example, a layer that performs a specific type of signal processing or a layer that operates on graph-structured data in a unique way. Normalization layers, instead of batch norm or layer norm, introduce a novel normalization scheme based on different statistical measures. Attention mechanisms, create a new attention mechanism based on a novel similarity measure. 3. Examples of crazy math ideas and code. Let's look at some specific, albeit somewhat hypothetical and potentially impractical, examples to illustrate the concept. 1. A fractal activation function ***. The idea is to create an activation function based on a fractal-like function. Fractals often have self-similar patterns at different scales, which might help the network learn features at different levels of abstraction. Explanation This code defines a fractal activation function. It iteratively applies a sign-based transformation to the input. The number of iterations controls the complexity of the fractal-like pattern. How to use in a neural network, TensorFlow/Keras. Explanation We create a custom Keras layer called fractal activation. The call method defines the forward pass of the layer. Get_config is essential for saving and loading models that use custom layers. We then integrate this layer into a simple Keras model. 2. A quantum-inspired loss function This is even more speculative. The idea is to borrow concepts from quantum mechanics to create a loss function that encourages the network to explore different potential energy landscapes. This is a very high-level concept. Here's a simplified, symbolic representation. Explanation The quantum_loss function combines a standard cross-entropy loss with a quantum potential term. The quantum_potential term is a very simplified approximation. In actual quantum mechanics, it's derived from the wave function, which would be represented by your network's predictions here. TF.gradients calculates the gradient of the predictions with respect to the true labels. This is a very rudimentary way to try to capture the shape of the probability distribution. It is computationally expensive and could be numerically unstable. The potential_strength controls how much influence the quantum potential has on the overall loss. Important considerations This is a highly speculative idea. The connection to actual quantum mechanics is very loose. Calculating gradients of gradients can be computationally expensive and numerically unstable. The interpretation of the quantum potential in this context is not straightforward. It's more of an inspiration than a rigorous application of quantum mechanics. 3. A hypercomplex weight initialization Idea is to initialize weights with quaternions, octonions or other hypercomplex number structures instead of real numbers. This could provide different gradient flow characteristics due to the properties of hypercomplex algebra. Explanation The quaternion_init function generates random quaternion numbers. Quaternion dense is a custom Keras layer, similar to the fractal activation one. It handles the multiplication of input with a quaternion weight matrix. The build method creates the quaternion weight matrix self.w and initializes it using quaternion_init. The call method performs the quaternion-based linear transformation. Using tf.complex for representing quaternions here is a workaround. Ideally, one would define custom quaternion data types and operations, which is more complex. 4. General steps for testing custom math. Here's a structured approach to testing these kinds of ideas. 1. Start simple. Begin with small, isolated experiments. Don't try to build a complex model right away. Focus on understanding the behavior of your custom math element. 2. Unit testing. Create unit tests for your custom functions and layers. Verify that they produce the expected outputs for various inputs. Check for numerical stability, example avoid division by zero, handle large/small numbers gracefully. 3. Toy datasets. Use simple, synthetic datasets, example XOR, spirals, linearly separable data, to test your ideas. These datasets allow you to easily visualize the decision boundaries and understand how your math is affecting the learning process. For visualization ** visualize the outputs of your custom functions, the gradients, and the activations within the network. This can help you identify any unexpected behavior or potential issues. 5. Controlled experiments * When comparing your custom math to standard approaches, run controlled experiments. Keep all other factors constant, example network architecture, hyperparameters, and only vary the math element you're testing. 6. Metrics * Use appropriate metrics to evaluate the performance of your model. Consider both accuracy and other metrics that might be relevant to your specific problem, example precision, recall, F1 score, AUC. 7. Statistical significance * If you're making claims about the superiority of your custom math, perform statistical significance tests, example t-tests, to ensure that the observed differences are not due to random chance. 8. Complexity analysis * Analyze the computational complexity of your custom math. Is it more or less efficient than standard approaches? Consider the trade-offs between performance and accuracy. 9. Gradient checking * Implement gradient checking to verify that the gradients calculated by your custom functions are correct. Numerical gradient checking involves approximating the gradient using finite differences and comparing it to the analytically calculated gradient. 10. Parameter tuning * If your custom math introduces new hyperparameters, carefully tune them to optimize the performance of your model. Use techniques like grid search or Bayesian optimization. Practical considerations. * Computational cost * Custom math can be significantly more computationally expensive than standard operations. Consider the impact on training time and memory usage. * Numerical stability * Be very careful about numerical stability. Custom math can introduce new sources of numerical errors, example overflow, underflow, division by zero. * Backpropagation * Ensure that you correctly implement the backpropagation algorithm for your custom math. The gradients need to be calculated accurately for the network to learn effectively. * Framework support * Make sure your chosen deep learning framework, TensorFlow, PyTorch, supports the operations you need for your custom math. You may need to write custom kernels in C++ or CUDA for optimal performance. Reproducibility * Pay attention to reproducibility. Use fixed random seeds to ensure that your experiments can be replicated. 6. Important cautions and caveats. * Most of this is unlikely to work out of the box. Expect to spend a lot of time debugging, tuning, and refining your ideas. Theoretical justification * Before you start coding, try to develop some theoretical justification for why your custom math might be beneficial. This will help you focus your efforts and avoid wasting time on ideas that are unlikely to succeed. Simplicity is key * Don't overcomplicate things. Start with simple, well-defined ideas and gradually increase the complexity as you gain understanding. Documentation * Document your code thoroughly. Explain the motivation behind your custom math, the implementation details, and any limitations. This will make it easier for others to understand and build upon your work. Reproducible code * Make sure your code is well documented, easy to understand, and reproducible. Share your code with the community to get feedback and potentially collaborate with others. Overfitting * Introducing novel math can easily lead to overfitting, especially if your ideas introduce new degrees of freedom. Employ strong regularization techniques and robust validation strategies. In conclusion, experimenting with custom math for neural network tuning is a challenging but potentially rewarding endeavor. It requires a solid understanding of deep learning principles, linear algebra, calculus, and numerical methods. By starting with simple experiments, carefully testing your ideas, and paying attention to practical considerations, you can increase your chances of discovering novel techniques that improve the performance, efficiency, or robustness of neural networks. Good luck and have fun exploring.